Okay, let's go ahead and talk about a classical result from diffraction theory that comes right from our lecture last time on rectangular apertures. So if you'll recall in that last lecture, what we did, we had a source, we had an observation point, and we had this perfect diffracting screen with a rectangular hole cut through it. It had a length and a width. And this screen doesn't let any radiation through. We approximated this condition with Kirchhoff radiation conditions, which says that the incident field here, or Kirchhoff boundary conditions, the incident field here along this aperture is whatever the source field, incident field would be in the absence of an aperture. And whatever the field strength is here on the screen is 0. So that's an approximate boundary condition, but it gets us started in the right direction. And then we use the Kirchhoff-Helmholtz integral theorem to calculate what the field solution is at that point. And we had a special way of solving it using the Fresnel approximation for phase, which lets you get much closer to this area, to this aperture, than the far field approximation that we often use in antenna engineering and other problems. It's still an approximation, but it works pretty well. So what we're going to do is take this aperture and stretch it infinitely in 3 directions, leaving only one area intact. And what we get is a half plane, an infinite half plane, and we'll be able to estimate the effect of just that diffracting half plane on the signal strength from source to point of observation. So let's go ahead and do that right now. Okay, here's our problem. Basically, here's our coordinate system. This is now looking at the infinite half plane from the side. Call this a diffracting knife edge. It's a infinitely thin, perfectly blocking material. Kind of like if you had like a piece of metal, a sheet, a piece of aluminum foil, and you had either light or radio waves coming electromagnetically close to the edge. What would happen? So the sight line that we pick for this problem is going to be, here's our point, source point, here's our observation point. And we're going to orient this problem so that the origin is along that sight line. And D is going to be the clearance distance. Between the origin and the diffracting knife edge. That's going to be an important thing to look at. Now if we go over here, it's important to realize you can have negative clearance distance, and what that means is that the diffracting knife edge is actually protruding past the sight line, such that the line of sight component is completely blocked. Now, for the rectangular solution, what we defined is the corner points of that square aperture. Said horizontally, we had one x1 and x2 represented this dimension, and then y1 to y2 represented this dimension. And it's interesting to note that this is really based on the classical knife edge treatment, where the z-axis is oriented perpendicular to the diffracting plane, and x happens to be up in the air, and y actually happens to be horizontal. It's very different from how we normally do it, but if you look at a classical treatment of this problem, like in Born and Wolf, you find that this is how they've oriented things. So our result last time said that if this were a square aperture with finite width and length, then I would get a component that would behave in terms of phase like a line of sight component, J, amplitude of my field, linear phase taper based on the entire length here, divided by the length itself, 1 over r, total distance, r naught plus r, attenuation of field, which of course is 1 over total distance squared attenuation of power, so that checks out. And then we have this term here that was based on cosine and sine integrals. And these u1s and u2s and v1s and v2s are all geometrically based normalizations of the coordinates of the distances here. x1, y1, x2, y2. So, now let's go ahead and take the limit as x2 goes to infinity, y1 goes to infinity, and y2 goes to infinity. So all of these limits, as the distances go to infinity, x1, x2, y1, y2, u2, v1, v2 also go to infinity, which means we're going to take these cosine integrals, sine integrals, and evaluate them at infinity. And when you go to positive infinity, and I should make a distinction here, this one should go to negative infinity because we're stretching the edges as far as we can make them. So what this means is that these guys will all go to positive or negative 1/2, depending on the sign of the argument. Let's see, should be minus infinity here. So when we do that, this is what we're left with. We have our standard propagating wave expression, but then there's this 1/2 minus j 1/2 cosine integral with this algebraic argument, and the sine integral with this identical algebraic argument. So what does this look like when we plot it on a graph? So here we've got clearance distance. Remember, positive means that your sight line is past the clearance distance and there's no blockage. Negative clearance distance means there is a blockage. And on here we have the field amplitude, and I've plotted it on a logarithmic scale. This is 10 to the minus 3. And so if you look at this value here, you'll notice that at the point where you go from blockage to unblocked line of sight, that's a nice demarcation of some wild behavior here. On the right-hand side, the field goes through and there's this oscillatory behavior. And one of the explanations for that is when you're in this line of sight region where your source and your point of observation is above the sight line, then you send a wave there, and there will be a diffracted wave off here that, depending on how far and up and down this protrudes, will create different levels of constructive and destructive interference. And that's what we're seeing here, which constructive and destructive interference becomes less pronounced as the obstruction is moved lower. And that kind of makes sense. In fact, if you let this go to infinity in that direction, then you should completely flatten this out. And you get straight line of sight propagation as if that diffractor wasn't even there. In fact, that gives you an idea of what the geometrical optics solution for this would be. It should be a flat line, and then all of a sudden you fall off the table. But you can see that with this physical optics solution, you get some diffraction behavior. You see some big constructive peak interference, and then even before you get obstruction by that edge here, you start to fall off the table. And on this logarithmic amplitude scale, the diffracted field just dies very, very quickly, to the point that you're 2 orders of magnitude down here with a 50 lambda protrusion into the link. And I think the link itself, the way that this was set up, remember there is a dependence on R0 and R. This scenario is described in the notes. R0 is equal to R0, R in this example. And the distance is like 100 wavelengths or something. So you can kind of get a feel for the values of these types of problems. You know, if this is in field amplitude, we've experienced almost 2 orders of field magnitude difference, which is going to translate into nearly 4 orders of magnitude of power difference. That sounds like a lot, and it is a lot. It's a serious reduction. Diffraction is a very lossy phenomenon. But if you think of this in terms of communications, let's say I had a transmitter and a receiver, and I had something jutting significantly in the way so that I was operating somewhere here on the diffraction curve. That might lead to, say, 30 dB of losses. And that sounds like a lot, but if you had, say, negative 60 or negative 50 dBm of received power, and you lost 30 dB from that, so that say you had now negative 80 dBm, dBm being decibels per milliwatts, then you would still have enough power for communications. That's plenty of power to get bits for a voice call or a data transfer reliably downloaded. So this is kind of the importance of modeling diffraction in some mobile radio scenarios, because there's often enough received power to still do what you need to do. Now, one thing I wanted to do before I finish this explanation of the Fresnel diffraction formula for knife edges is to look at something, and we're going to do a little compare. Let me go ahead and drag and drop the solution here. so that you can see. There we go. Now, let's look at the argument of these cosine and sine integrals. First of all, you see that it's really d cosine theta, which is the only clearance distance dependency. And that kind of makes sense if you think about it geometrically. D cosine theta is really this distance d prime, from the edge of the knife edge up to the perpendicular sight line, point on the sight line. And so we would get the exact same result if in this particular problem, the way that we've defined it, I were to draw the knife edge tilted like this, which is the original problem, just tilted by theta degrees, or if I were to draw it straight down, or over here, or over here, or over here at an angle. And that kind of makes sense because the basis of our Kirchhoff boundary condition said that this wave is going to keep on doing what it's doing. It's going to get to this point, and we're basically just going to chop it off. And then it'll keep propagating to this point from there onward. So that kind of makes some intuitive sense. Now keep in mind, when you do reintroduce realistic boundary conditions more precisely, then there is a dependence not only on the composition and the polarization of the interaction of this wave with the half screen, but its angle and even its thickness. Like according to the Fresnel formula, this could actually be a wedge, a blocking wedge instead of a knife edge, and you get the same result. But in a precise electromagnetics problem, the width of this wedge, the angle between the facets of the wedge, actually affects the radio wave propagation and the diffraction solution. But this is a really good first order approximation. The other thing I want to do is preview an idea here. And that is, let's look at the distance from the source to the edge, which is this line right here, and then the distance from this edge to here, which we're using the Pythagorean theorem to calculate these. This is not anything particularly surprising. And we're going to subtract from that the distance from the source point to the observation point. So we're looking at the path distance from here to here, minus from here to here. And that gives you this expression approximately. And we're going to approximate it further by doing a little Taylor series. So we're going to approximate these square roots by Taylor series. We can do that if this distance here is much smaller than the total distance, r and r naught. And if I do that, my Taylor approximations make it so that when I subtract that out, my delta r, the distance in the path length, is only a function of d prime squared over 2, 1 over r naught, plus 1 over r quantity. And I can write it like this if I want to, by basically solving for d prime, putting everything on the left-hand side and taking the square root. So then what happens if I put d prime back into the argument here for my cosine integrals? Well, I have 2 r naught, r, delta r, r plus r naught, times r plus r naught, when I take this term down, r naught times r naught. Well, this is very interesting, right? Because we basically, when we multiply these two together in the argument, this cancels, This cancels. This cancels. And what we really have is 2 wave number over pi times delta r. And that's very interesting, because what it's really saying is that that path length difference between the diffracted ray, so to speak, or the diffracted path, minus the direct path, is the only thing that modifies what would be a free space result. And we'll use that in the next lecture when we talk about practical applications of the knife edge formula.